and then electric fields and magnetic, and then DC motor, of course. Okay, give it a try. All right. So we'll start with the gravitational fields. Remember, the gravitational field is, the origin of the gravitational field is coming from a mass. Of an object. Gravitational field. As you guys remember, if you think about the field line, in gravitational fields, always the field line is coming towards the objects, attractive. The gravitational field is always attractive. But with the distance, the gravitational field strength is decreasing. Okay, so gravitational field, these are the field lines. They are static but non-uniform. Static means they do not change with the time. Does not change with time, but non-uniform. That means it changes, varies with the distance. Okay, so that's the gravitational field. Now we'll talk about the Newton's universal gravitational law. So if you have two objects, capital M, or maybe say M1, M2, the distance from center to center, that R is the distance from center to center. Okay, distance from center to center. Then there is an attractive force acting between the two. They are coming from Newton's third law. So this force is proportional to the masses and inversely proportional to the distance squared. So that's quite important. So with that, M1 and M2, but the force is inversely proportional to the distance squared. So when you combine these two together, you get this relationship. I think you guys are quite familiar with subbing the numbers into this equation and get the answer. So 6.67 times 10 to the power negative 11, that's the constant. So keep an eye on this inverse square law relationship. Inverse square law relationship that tells you that the force As I said, gravitational force may be, if I say Ft, inversely proportional to the distance squared. So if I have the object, two objects at a distance r, so this is the m1, that's m2. If the force is F, if the distance is doubled, then the force becomes 1/4 2 squared, quarter. If you look at the way that the gravitational force varying with the distance, we can just put some numbers, say, if there is, say, 1000, the force is 1000. If you're looking at a distance, so say this is at the center, and then if you increase, or maybe say just say r at the surface, that's 2r, 3r, 4r, and so on. You can see if we double the distance, this will be decreased by a factor of 4. So it's become 1000 divided by 4. You got 250 somewhere here. So I'm just trying to put into context. So your, let's say at distance r, the gravitational force is 1000. If we double it, this becomes 1000 divided by 4. If we triple it, 1000 divided by 2 squared, 3 squared, and if you 4 times, 1000 divided by 16, and so on. So that's what you get. Your graph looks like that. Never reaching the asymptote. You can see it's gradually getting smaller and smaller because it's following the inverse square law relationship, inverse square law. Okay. You guys probably remember this question about asking a place where, maybe if you guys can have a quick look, maybe I'll just go back to the gravitational field strength as well. So anyone has any problem calculating if you know the masses between the two and the distance and calculating the gravitational force? I wouldn't think that anyone have problem with that. Yeah, just a matter of converting kilometers to meters, or be careful if they give the masses in tons or whatever. Apart from the units, I don't think you have any issues simply calculating that, the gravitational forces. Okay, let's check the gravitational field strength. The main thing, the inverse square law relationship here. Inverse square law relationship here. Let's check, what did I say here? Yeah, the gravitational field strength is the same. That's a little g. Oh, that's the same as the gravitational acceleration. So the gravitational field strength, little g, is defined as is the gravitational force per unit mass or 1 kilogram mass from distance at a distance r from the center. So we guys all know that. So gravitational force can be written as the mass times the gravitational field strength. Okay, mass times the gravitational field strength. Then if that can be written as capital M, that's the one that produces the gravitational field, the little mass somewhere, distance squared, and then you get this expression for little g. So little g, again, it's obviously inverse square law, but the field produced by one single mass. That's the object. Am I cutting off? That's two, you can see. That's the capital M. So that's the distance r. So if you want to find the gravitational field strength at that point, M is the central mass, you get the distance r squared. Okay, it's obviously inverse square law. Again, there's a graph, and there's a question, page 3, if you guys want to quickly work it out. Page 3 in that like a revision booklet I sent. If you have a look, page 3, and that PDF, page 3. In terms of the units, guys, units, newtons per kilogram, or you can use mass, meters per second squared as well. If we just quickly look at that question in page 3, a 5 kilogram object placed 2r from the Earth center, that's r, 2r means another r, from Earth center. How fast would accelerate towards the Earth? On the surface, the value of g is 9.8. So they're asking g dash there. So if you want, you can write, but by looking at the value, you can say it's double the distance. It should be a quarter of the original one. But you can simply say g is inversely proportional. So gm on r squared, and then you have g2 gm on twice that. If we take simple ratio between the two, g1 on g2, Then when you simplify it, the 2r comes to the top. Division when you convert it to multiply. Then what you get is 4 at the top. Or you get that your G1, which is at the surface, is 4 times. Or you can just do it simply from your head. It's going to be 1/4 of what you had before. That's the gravitational field strength. So that's the acceleration. If they're asking as acceleration, that would be the acceleration. Something like that. At distance, how much would it weigh? The weight going to be mg. The mass doesn't change. That would be the new weight there. 12.25 or something. You guys can draw that graph. The graph should look like once you plot it. So you can start from the radius of the Earth around 10. That's RE. Goes like that. Now, you guys all comfortable with this stuff so far, yeah? Anyone want me to go through a bit slower? Yes? Okay, so you guys okay, yeah, this stuff? I'm just rushing a little bit more. Yeah, okay. Now, if you look at the graph, guys, for gravitational field strength versus distance graph, the shape is pretty similar, like a force-time graph. This is at the surface of the Earth. It drops following that inverse square law. Inside the Earth, it decreases linearly. This part is inside the Earth. That's inside the Earth. It goes linearly. If anyone wants to see why that's doing, you can work it out. So assume that density of the Earth is uniform. So the mass of the Earth can be written as the density times volume, because effective mass is decreasing. So the density times volume is the volume. And then become pi r cubed. So then your GM become, you don't need to know, so GM on r squared. Since they give this question like a couple of years ago, the capital G, your M become 4/3 pi r cubed over r squared. You can see that simplify into kind of linear relationship here. This is inside the Earth. So G becomes 4/3. These are all constants. G pi times r. It's linear, like y equals mx type. It's linear inside. That's inside the Earth. That's why it's dropping. But here it's follow the inverse square law. The rapid dropping, it follows the inverse square law. You guys want to quickly work it out? Some few questions in page 4. Then move on. Page 4, give it a try. Few questions on page 4. Inside the Earth, since they give this diagram, the graph in, is it last year, year before? It's, oh, maybe last year. So just better off, like, need to know, like, roughly how do you get that shape inside. Okay. Next thing, some people may assume that because of the moon's gravity is, let's look at the question in page 4 very quickly. Moon's gravity is 1/6 of Earth. Would mean that moon is 1/6 of Earth mass. Using the following data and the equation for G, calculate the moon's mass. So they ask you to calculate the mass of the moon. So the G at the surface of the moon is the Earth's gravitational acceleration divided by 1/6 of that. This is moon. GM means that's the gravitational field strength of the moon. That's the gravitational field strength of the Earth. The radius of the moon is given. (1,740 kilometers). And also they gave the mass of the Earth just to compare. So we're trying to find so we can use, this is the gravitational field strength of the moon. We're trying to find the mass of the moon and the radius of the moon square. Right. So this value is 9.8 divided by 6, which is, they simplify that, they're giving it to be about 1.6 newtons per kilogram. Is that right? 9.8 divided by. Yep, 1.63. If you want to be precise, 1.63. And then 1.63. -11. We're trying to find the mass of the moon. Remember to convert the kilometers to meters. And you square it. And you solve for mass of the moon. Times squared divide by -11. So you get like 7.4 approximately. 10 to the power 22 kilograms. Okay, you guys okay? Yeah? So can you explain the first question again? Sorry. Oh yeah, you got it. Okay. Okay. They're asking what's the ratio of the mass of the Earth versus mass of the moon. So part question number 2, mass of the Earth over mass of the moon. Put the numbers in. 5.98 times 10 to the power 24 over 7.4 times 10 to the power 22. when you look at the ratio, it should be about, I don't have a number. But 81, it's about 81 times bigger. The Earth is 81 times bigger than, so these questions we considered difficult? Not really, no. These are simple ones. Why you guys finding it difficult? I mean, I'm just going through the basics of it just to cover. No, I wouldn't think these are hard ones. Next thing. Now, when a star is dying, it can convert into a neutron star. Neutron star could be a star with a very small star. Diameter could be like 100 or 10 kilometers, very small. But the mass could be same mass as the sun. You can see enormous gravity. Okay, and next step would be the black hole. So that means it's shrinking further. So when you shrink further, your gravitational field strength can go undefined, like infinite. So they're talking about so the diameter toward the end of the life, Newton's law, consider our sun. So the gravitational field strength of our sun is, they say, 273 newtons per kilogram. Mass of the sun, radius of the sun, say giving. What they asking, I forgot to show. Okay, so we have to show that. Right, just give a quick calculation and find what's the gravitational field strength of the sun. Which is gm1r squared. The mass of the sun is about 2 times 10 to the power 30. The radius, it's in kilometers, guys, need to convert into meters. Ten to the power 8 squared. This is the question 5.6. Okay, so it has an enormous mass. We're trying to calculate the gravitational field strength of the sun. Next step would be, when we're considering the same star going to be a very small diameter, you get like 273.41 something. Hey guys, in the exam, just need to show all these steps. If they ask you to calculate, you have to show these numbers. You get 1 mark. Don't just simply write and go to the step straight away. You will lose 1 mark. So the next part, now they're saying that the mass is now 400 times smaller. Our radius is 400 times smaller. The new radius would be the original radius of the sun is 1/400. 400 times more. Minute. Yeah, correct. That's correct. That's correct, because just going through the theory is not going to be helpful, yeah. Because if you do a couple of questions, that comes to refresh your memory a bit better. That's what I was thinking. Rather than just, if you do theory, it's going to be boring, right? Hey guys, if the radius is 1/400, you can straight away say they're asking the gravitational field strength, the new one, because it's proportional to r squared, yeah? If you reduce the new one would be 400 squared times bigger than the original one, because the inverse square law, your radius is 400 times smaller. Or if you want, you can write like an equation here. Okay, let's write. You're comparing the two. So G1 on G2 R2 squared on R1 squared. You can use it like equation, derived formula. So G1 is 273. We're trying to find G2. R2 going to be original one divided by 400. This is R squared. When you simplify that, what do you get? So I'll just go to 273 over G2 R squared. This is 400 squared when you simplify, and then your R's will cancel. Your new G2 going to be, people who can see it, you can just straight away say that it's going to be 400 times bigger. That will be the new field strength, 400 squared times 273. It's going to be enormous. I think the answers are not matching this for the 5.5. 367, 4.37 times 10 to the power 7. Almost like a black. Yeah.
Excuse me, Derek.
Yep.
How much working out would you need to show for this question? Because I just I just showed the G2 formula.
Okay, so
G2 is equal to 400 squared.
at least if we can show that your G is inversely proportional to R squared, at least you mentioned saying that you understood the concept, physics behind it. Therefore, the new G2 or new G2 is equal to 400 squared times the original one. If we can show that, that probably something, but just need to show that you understand what's going on in terms of physics. Does that make sense?
Yeah, I think that makes sense.
What happened to the value of G as R reaches infinity, R reaches zero? Remember, don't compare, use this equation like I'm talking about question number 3. Don't treat the normal Earth with that equation, thinking that if I ask you to find what's the gravitational field strength at the center of the Earth, don't assume that it's infinite. It's not. is becoming zero. But here we're talking about a black hole where the radius is like the whole thing is shrinking, getting smaller. Massive condensation of mass. Okay, neutron star is the same mass like a sun, but the radius is like 10 kilometers. You can imagine what's the gravitational field strength going to be. Now the black hole radius is almost zero. That means you're shrinking to a tiny dot there. But the mass could be the same as the original mass that you had, or maybe slightly lower. So you can see a massive amount of gravitational field going to suck everything in. All right, we'll move on. I don't know, this is the question about, I think probably you guys remember, there is a position. I'm just talking about question in page 5. Any question, guys, on this? Anything not clear? How are we getting this 400 times thingy? 400 squared? You guys are reasonably comfortable? If the radius is half, your gravitational field strength will be increased by a factor of 4. If the radius is reduced to 400, so your gravitational field strength increased by 400 squared. So the next thing, this is a question that came up quite often, but I haven't seen in the beta coming up. Just to safe side, since seen in textbook and here and there, just maybe not a bad idea to practice that question. The question is, this is the Earth. So that sometimes the VCA tends to put question, like if you see same question coming up in trial exams, papers, you can certainly see that it's VCA picking up and they'll just change the numbers. That question comes in. So that's the moon. The distance between that is 380,000 kilometers. We'll assume it's center to center. But it's just showing like a surface, but assume from center to center, otherwise it's a bit difficult. So there will be a point where, let's assume like a spaceship or something traveling. You guys probably remember this question. The gravitational pull by that spaceship, by the Earth, by the moon, they cancel each other. Basically, net force due to the gravity is zero at that point. So they ask question, they're asking, what's that distance? Let's say x is that distance. For convenience, let's say this value is r minus x. What you guys have to do is try two expressions. Person to ask question, can you give an example answer for question 3? What would you need to, what do I need to mention? Is that the same question? Oh yeah, what happened to the, oh, okay. Yeah. So because like say at the end of the star's life, yeah, so it can be a way of finishing up the life is like becoming a black hole here. The question 3 is just asking what happened to the value of g, little g, gravitational field strength, when the radius reaching to 0, that means you get into like a single dot. So this is what believed to be the cause of black holes, incredible density. So that means, so you have a very tiny, radius is almost insignificant. So this is where at this time you can interpret using this equation where r becoming 0. When you put, then the g goes to gm on 0, yeah? That's becoming finite. So the gravitational field strength become very, very high. Okay. Yeah, quite stronger. Maybe just sub the numbers, like say when r tends to 0, the g just put that, say reaching infinity or undefined. Okay, reaching infinity. So therefore, the gravitational field strength become very extremely large. So you can't really define what's the size of the gravitational field strength. Guys, if you go back to this question, right? Okay, so when the question saying the gravitational forces cancel at x from Earth, cancel, that means the gravitational force exerted by the Earth equal and opposite the gravitational force exerted by the Moon. This is Earth. Okay, maybe just put Earth. Let's assume the mass of the spaceship is little m. Write two equations for the gravitational pull on the spaceship. So capital G, mass of the Earth, mass of the spaceship, divided by x squared. Since it's the ratio, we can just live with that. Your final answer will be in kilometers. That's the mass of the Moon, mass of the spaceship, r minus x squared. Get rid of all these common values. Then you have a simple expression. The trick is don't expand it. Bring all the square terms into one side. You will have two solutions. One solution comes outward, outside that range if we take the negative answer. So that's the mass of the Moon divided by the mass of the Earth. So what you can do, as you guys remember, the ratio was 82 or something, like we worked it out before, is it? Or is that the... Yeah, I think we worked it out in previous question. The ratio was 82. ME on M Moon was 80 or 81. So if not, if you guys just work through, we're trying to find, I can toggle back. I just swap it. ME on M Moon. If you look at the ratio, the mass of the Earth is 5.98 and mass of the Moon is 7.234 10 to the power. I'm pretty sure like we worked it out, it was like 81 or 81 point something. Then I can sub that one in here. Then take the square root. Take the square root of either side. And you get x r minus x 9 or negative 9. Then expand it. Okay. Then you can see that your x is going to be 9/10. 10, yep. And if we expand here, then you get negative 8x. Right? Negative 8x, negative 9r. Then you can see your x is more than r. This is not possible. This is, you're getting x, so we can ignore that answer. Just focus on that. That's going to be 0.9 times the original value. It's 9, so that's pretty close to the moon. Yeah, because they are asking to explain simply asking to explain. They are asking what happened to the value of G as R reaches 0. The main thing is use the equation to show your thinking. The equation is G equals GM1R squared. When the R reaches 0, your G, gravitational field strength, reaching infinity. That's the main thing that you need to show. All right. You guys need to practice quite a bit, a little bit on energy in gravitational fields. Get it under the graphs. This is, I would say, if they give you that question, I'm pretty sure that will be like a differentiating question. Some kids will forget the method, some will come up to a certain point, some people get half the marks. Some people struggle simplification afterwards. I think if you expand it, you get a quadratic. Still, you can do it, but I think it's getting messier. You better off keep the square terms and then take the square root on either side. Would be the easier way to do it. But yes, if you can expand it and get the quadratics, not the end of the world. You can still do it.
Yeah.
Yeah.
Why did you divide it by 10?
Divide by 10. Oh yeah, okay. So bring the 9x to the left-hand side. So they become x plus 9x, yeah? So this is 10x. It's become 10x equals 9r.
Yeah.
So the x becomes 0.9. Okay. Okay, we'll move on to the energy. The change in energy. You can have two types of graphs, guys. Two types of graphs. One is the force, gravitational force versus distance. The second one, gravitational field strength versus distance. Gravitational force versus distance, easier because area under the graph straight away will give you the work or change in energy. You don't need to times by the mass of the object or anything. So if that is moving from one distance to the other, the area under the graph, unfortunately, you have to count the squares in some cases. Area under the graph, you don't need to times by the mass because it's a force time graph. Area under the graph will give you the change in energy. Either when you're moving away, you're gaining gravitational potential energy. When you're coming close to the object, you're losing GPE but gaining kinetic energy. So maybe make a note somewhere. It's the same scenario like if I'm dropping my pen from certain height. So it's losing gravitational potential energy, it's gaining kinetic energy. We can't use constant acceleration equations because your little g is continuously changing. That's why we need to consider the area. Coming towards the Earth. That's how we write. Loses GPE, but gain kinetic energy. So quickly make up the simple example. Some space, some debris, some junk coming from a certain distance. It's about 500 kilograms. Coming at a speed at the moment 3 times 10 to the power 3 meters per second. Okay, it's coming from somewhere here. Okay, it's coming from a certain height. Maybe it's coming from, maybe I'll just make up a grid quickly. It's not ideal, but it's okay. It's coming from traveling towards the Earth. Okay, from that to 8 times 10 to the power 6. So we'll break up, maybe just make it 12 because it's better. So it's coming from here to here. All right. So it's coming from that to that. Find the lost GPE. When it's moving from, well, I'm saying 12 times 10 to the power 6 meters to, because remember it's speeding up, it's losing its gravitational potential energy. Distance. It's moving such a distance, it's losing its energy. So lost GPE, you can easily work it out. Why isn't 9 possible? Oh yeah, because why is not possible in the previous question. So that means your spaceship should be here, yeah? Because your x becomes 9 over 8 means more than 1. 9 divided by 8 means 1.125 by distance r. That means spaceship should be there. So that definitely will have a greater force by the moon than that. It's completely outside our region. We're looking at a point somewhere in the middle, but our answer says it should be outside here. That's why it's not possible. Okay. Yeah, it has to be less than 1. Find the lost GP when it's moving from that to that. So the area under the graph. But now you don't have to, because it's a force, guys, it's a force. Lost GPE. So you have to count the squares, see how many, roughly how many squares are there. So that means we have to count the squares. Times by the value of 1 square. So I don't know, just roughly just say 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7.25 or something. I'm just making up this many squares. Value of 1 square going to be 1000 times 6 times 10 to the power 6. Oh no, actually it's 1, should be 1, should be 5. It's the increment of 1. Be careful, that's another thing you have to be careful. Look at what the increment is. Sometimes you can get into the wrong value. Each block is 1 times 10 to the power 6 by 1000. That makes sense for this block. Each block, that's 1 times 10 to the power 6 times by 1000. So that's going to be 7.25 10 to the power 9 joules. That's the lost or gaining. This is equal to gain in kinetic energy. They can ask you what's the new kinetic energy. How are we going to time? Oh no. Okay. I'm going very slow. Okay. So the new kinetic energy is part B. Find the new speed. So the new kinetic energy is the original kinetic energy plus the gain. Okay. The original speed was, I said, 3 times 10 to the power 3. Half times the mass was 500. 3 times 10 to the power 3 squared. That's the original speed. That far. Plus 7.25 times 10 to the power 9. So new kinetic energy going to be half times mass times v squared. Okay, so you have to solve it, and can I leave it to you guys? Yeah, solve for v. Solve for v. We are just a little bit of running behind. How are you guys going with these graph questions? You guys are generally okay, generally not okay. There's a big chance that you get a question. There's a big chance that you get a question. Yeah, K plus two as well, yeah. If you guys listened, okay. How about other guys? You guys are feeling okay with, can we skip or you want to do it? Okay, do it quick. Get through this question. This is the Halley's Comet. So they came through close to the Earth in 1986. It's not going through like circular orbit, it's just going some oblique, some funny movement. So the question is, the path of this comet is elliptical. Yeah, elliptical. Part of this ellipse is shown below PQR, representing 3 points. Point P is 1 times 10 to the power 12. Calculate the gravitational field strength. Now you guys need to do that. Just do it quick. Use the equation, little g, gm on r squared, and then work it out the next question, next part. This is the question, page 7. So the comet is somewhere here. Like that. So that's 1 times 10 to the power 12. Calculate the gravitational field strength at that point P. Okay, 6.67, negative 11. What's the mass of the, we're going around the sun. Mass of the sun is 2 times 10 to the power. Always the central mass. Central mass divided by 12 squared. Should get a value of 1.33, negative 4. Now they're giving the gravitational force here as well. If they give the gravitational field strength, guys, you need it times by the mass. So it's moving from 10 to the power 12. The diagram below shows the gravitational force that the sun exerts on comet as a function of distance from the sun. So 10 to the power 11. Estimate the increase in kinetic energy travel from 3 times 10 to the power 11 here. It's pretty similar to 1 times 10 to the power 11. Again, count the squares, guys. So we need this area. When you come from here to here, they ask you to find increase in kinetic energy. Or basically change in kinetic energy. Area. So count the squares. Times by the value of 1 square. Count the squares times by value of 1 square. Okay. Says like about 4 squares. I don't know what to count. You guys count it. Roughly about 4 squares. Times by, you need to count how many squares, the value of 1 square. So the value of 1 square is 2 times 10 to the power 20. Because value of 1 square is equal to 2 vertical axis 2 times 10 to the power 9. Horizontal axis is 1 times 10 to the power 11. It's 2 times 10 to the power 20. Then you times by 4. That means 8 times 10 to the power 20 would be the total energy. Yeah, we're still limping. Okay, I think we had to move on to the satellites, guys. Yes, go through that. I put 1 or 2 questions, but if you guys having trouble, drop me an email or text or whatever. All right. Satellites. 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 So they're going on a circular path. It's a centripetal force. This is the mass of the central object. This is the mass of the Earth. When the satellites are orbiting around, they have only one force acting on them. Okay, their speed will be along the tangent. The speed stays constant, velocity is not. Only force acting on them is the gravity. Otherwise, without that gravitational force, it will go straight. So the gravity will pull back towards the Earth. Otherwise, again, trying to move forward on a straight line and again pull back towards the ground like that. So centripetal acceleration becomes the gravitational acceleration. Centripetal acceleration, same as the gravitational acceleration. So centripetal acceleration going to be v squared on r. The gravitational acceleration going to be gm on r squared. So when you simplify this, you get this expression for speed of the satellite. This, as I said, this equation is quite popular in recent times in the exams. Okay, it tells you that the speed of the satellite at a given orbit is independent of the mass of the satellite. Independent. Maybe this is, I said Vs is the speed of the satellite. Vs is independent of its own satellite's mass. It depends on the mass of the central object, and the radius. Central object and the orbital radius. So it's quite common saying that they are going to launch another satellite and then going to place this satellite in the same orbit as the previous one. Since it has a lesser mass or lesser weight, will that satellite will go at a different speed or slower speed or something? So always make use of this equation, justify that as long as you placing at the same orbit, the speed of the satellite remain the same. Same orbit, same speed. Okay, same orbit, same speed. Because it does not depend on the speed of the mass of the satellite. Right, just have a look at Kepler's law. Also, you can use another equation for that scenario. Because the centripetal acceleration is given by that as well for any object, 4 pi squared on t squared. That's also equal to gm on r squared. That's simplified to Kepler's law. Okay, maybe just leave it there. Just say if you know g or something. So if you know period or radius, they ask you to find the g. There's another connection that you can find it out. Or you can say gm on r squared. Okay. Now we're going to look at Kepler's. This is Kepler's third law or satellite equation. To obtain the satellite equation, what you do, that's the mass of the Earth, that's the satellite. Be equating the centripetal force to gravitational force. O acceleration is fine as well. So centripetal force we can write m. Okay, so I can just write m times 4 pi squared on t squared. R squared. So your m's will cancel. So you left with now. I think I highlighted this. Your left-hand side is a constant. Left-hand side is a constant. So if I have a one orbiting system, say our solar system, there are so many different planets orbiting around. One orbiting system, they are at a different distance. So you can equate them because this part is a constant. I like that. For a given system, say example our solar system. Gm on 4 pi squared is a constant. Okay, example our solar system. Or maybe some moons around, or maybe our satellites, we can just orbiting around the Earth. Therefore, we can write this equation saying that Gm on 4 pi squared R1 cube on T1 squared, R2 cube on T2 squared, R3 cube on T3 squared, and so on. I don't know whether you guys remember this, yeah? Hopefully remember. Sometimes comes very handy. Comes very handy. Depends on the question. People are joining in thinking that we're doing the next bit, power transmission, and we still got stuck in the first bit. Okay, let's give it a quick try. Hey guys, now you have to have this derived formula in your cheat sheet because you're allowed to use it. You're allowed to use, say this is the general equation, 4 pi squared, R cube on T squared. And then you get this derived formula for the central mass. But double check, triple check whether you rearrange properly and do some questions and check whether your equation is correct before you write in your cheat sheet. And then R 4 pi squared GMT squared on 4 pi squared. That's another one. So you have to put this one in your cheat sheet because VCAT doesn't care. As long as you write this equation, you get 1 mark. So if you are a bit not happy, you can write that equation if you want, but they want this equation rearranged formula. And then you can write another expression for t. Is a cube root here, 4 pi squared r cube on gm. So these three equations you can put it in, plus gm on r. All right. Do you want me to go through some satellite questions, or you guys are only thing? Yeah, geostationary, yes, sure. Geostationary satellites. Now, I will get rid of this here. There are geosynchronized satellites, but we cover year 12, we using geostationary satellites. That means they have to orbit around the equator. Geostation satellites. Orbital period, the way that you're keeping at same position, because the orbital period is same as the rotational period of that central planet. A rotational period rather. Around its own axis. Sol is orbit around the equator. And move in the same direction. Planet rotational direction. Say for example, if I place the geostationary satellite around the Earth, this is the equator, it's orbiting around the equator. The Earth is rotating east to west, so that means the satellite also orbit around east to west. And then the period going to be 24 hours. I think you guys know, I think for the gravitational field strength before the equation, we wrote R1 R cube, was it? Yeah, R2, it's just other way around. So if you look at that, so G1 on G2 should be R2 squared on R1 squared. That's the previous one. I don't know. That's the original I gave. G1 on G2 was R2 squared on R1 squared, other way around.
Okay, thank you, sir.
Okay. Use its rockets to enter the high orbit. What change in terms of GP? Okay, so that means you put in some external energy. But if you use a spaceship to change the orbit, that means you're putting some external energy, but still you had to talk about in terms of the total energy. Total energy is a combination of GPE plus kinetic energy. It's true that you put in new energy into the system, but if you go to a higher orbit, you're decreasing your speed because we had to use this equation to say you're losing kinetic energy and therefore you're gaining gravitational potential energy. It's true that if you're putting external energy, but it's the total energy now is a sum of kinetic energy plus GPE. But if you go to a higher orbit, you're losing your kinetic energy and you're gaining more gravitational potential energy. I think that was a question. It's 2017, 2018. They're saying that they're using an external space probe to change the orbit or something. Yeah. I think just have a look at the weak answer 2018. I'm pretty sure 2018 could be another hemisphere. Okay. I might have put this question. Okay. Hey, how you guys are going with the satellite questions? You guys need to do a few satellite questions, or you guys are okay? Anyone want to go through satellite questions? All okay? Okay with me? Okay. I'm fine with just giving them. Okay. All right. Okay. Just move on to electric fields. We're going a bit slow, guys. Now just have a rule of thumb. If you're looking for the distance from the surface of a geostationary satellite, in case if you get a question, that's roughly about 36,000 kilometers. 36,000 kilometers. That's roughly the value that you should get for a geostationary satellite, 36,000 kilometers. If you use Earth information, the question can be a different planet, then you get different answer. But if the question was targeting Earth and asking about the geostationary satellite, then yeah, about 36,000. The period is 24 hours. I didn't say that. So period should be. Oh yeah. Oh yeah. I did. One axis. Okay. Electric fields. Okay. Now a charge like in gravitational field, we know it's the mass that producing the gravitational field. In terms of electric field, it's a charge that producing electric field. To find the direction of the field, we assuming there is another imaginary charge somewhere in the space. So the field lines are always going out from a positive charge. And closer the field line, stronger the field. If it's a negative charge, the field lines are coming towards it. It's a positive, negative. And how to draw the field lines. the drawing field lines. Electric field lines. Yeah, sure. Drawing of the electric field lines. So if I have a positive and negative, so that's a positive or negative individually. So they're going to attract each other. Always we're treating some imaginary positive charge there in the space. The field lines are going like that. The closer the field lines indicate the field is stronger there. So leaving, entering. Okay, so if I have opposite charges, they repel each other. You can see almost zero field, but you can see a strong upward field there. At the center, the field strength is almost zero, but there's a strong field upward, downward field there. Sorry, that's positive. Both are positive, they're repelling each other. Positive. They might ask you to draw 4 field lines or something. You can see the electric field strength upward here. These are the points that they can pick up and ask you questions. The middle is almost zero. So the field is stronger here. The closer the field lines, stronger the field. Okay, so if I have like a single, if I have a positive charge, and if it is negative, the field lines are going like that. Like if you have a plate, negative plate and a positive charge, that's how the field lines are looks like. All right, also, maybe just draw for the completeness, the uniform electric field. So obtain. Now, if they ask you whether these fields are static or dynamic, if you look at the individual field, they are static. They're not changing with time, but they are again non-uniform. They're changing with distance. They're static, but non-uniform. They're static, but non-uniform. Obtained by parallel plates. If you guys need a break, just ask me. So I was planning to have a break about 7:15. Let's see. If you guys can't tolerate that long, we'll just have a break early. If you connect that side to a positive battery, negative, pretty uniform at the center. Always field lines are going positive to negative. They're parallel between the two parallel plates. They're pretty uniform. At the end, they're a bit bulging. Okay. We talk about the other equations related to that. once you get this one's going. Coulomb's law. It's pretty similar to gravitational, universal gravitational law. Again, it follows the inverse square law. The force between two charges could be attractive or repulsive. In gravitation, law is attractive. Here you can have attractive or repulsive. Okay. Force could be attractive or repulsive. I mean, positive, positive, they repel each other. They attract. Positive, positive, or negative, negative, they repel. They repel each other. Okay, so Coulomb's law, that's not the Coulomb's law. Coulomb's law is the force between the two charges. The force between the two charges could be attractive or repulsive, as I said. Proportional to the size of the charge. Again, it's obeying inverse square law. When you combine these two together, you get the Coulomb's law. R squared, the K value. You guys know that. Okay. Right, so I'll just get rid of this. If you miss it, I'll try to get the record and send you this. Okay, so let's work it out, this question. So this is 30 microcoulomb, so positive. Okay, that's negative 20 microcoulomb. That's 40 centimeters. That's, say, 60 centimeters. That's 25 microcoulomb. This is positive, that's positive. A, B, C. Can you find the force exerted by A on B? C, give the direction as well. C on B. Find the net force on C. On B, sorry. Do you guys want to give a quick try? A on B. The K value. Two charges, 30 micro means 10 to the power negative 6.
So what's the charge of the last, the negative one?
Negative 20, this one.
Oh,
Okay, just work it out. I'll just drink some water and come back. So, A on B, give the direction as well. Don't put negative or positive sign, just look at the direction and tell the direction is left or right. -9, positive 9, -6, and the distance has to be in meters. That's in newtons. 10⁹ times by -6, 25 -6, divide by 0.4 squared. You get 42.14. Since it's not the last final answer, just keep few extra decimal places, and then finally rounding up. Actually, that's the answer, 42.14. C on B. This is to the, because they're repelling each other. This is to the right, because they repel. These two repel each other. That force going to be that way. And then between C and B,
so is that 60 meters?
60 centimeters. Sorry. 60 centimeters. Okay, that's also to the right because they attract each other. So 8.9. Divide by 0.6 squared. Get 12.486. Right. So you have two forces acting on the same direction. Therefore, the net force on B, you have AB as well as CB, both acting to the right. That means 4214 plus. You get 52.63 newtons to the right. You guys are okay to do these kind of questions, right? Anyone having trouble? This one is A and B direction is right. Yes, yeah. A and B is to the right as well as B and C to the right as well, because A and B repel, B and C attract. So overall, they're going to add up each other. What's the far right particle? Oh, okay, far right particle. Hang on. Sunraj, you managed to get it? Which one you asking?
Yeah.
Okay. Now we're looking for the electric field strength. When you define the electric field strength, it's the electric force per unit charge. any charge. F equals QE. So the F, so we have large charge, capital Q. We're looking for the field strength at a distance R. This is where your 1 coulomb positive charge, the electric field strength, even if you just KQ, Q1, Q2 on R squared, you can see one of the Q's cancel. You get KQ on R squared. It follows the inverse square law as well. You can get a similar question, but asking for the electric field strength at a given point. So if I make up a simple question, so that's a charge Q. It's 1.2 meters. So that point X, electric field strength at point X is say 14 newtons per meter. Newtons per coulomb, sorry, newtons per coulomb or newtons per meter. Both newtons per meter. Newtons per coulomb. So newtons per coulomb. So the electric field strength, you're getting F equals Q times E, F1Q, newtons per coulomb. Newtons per coulomb, 1.2 meters. That the field strength point Y. If the electric field strength equal to 12 newtons per coulomb, find the distance. Do you guys want to give it a try? So there's a point where in space somewhere at a distance R where the electric field strength is 12 newtons per coulomb. Here it's 40 newtons per coulomb. Find that distance R. Just follow the inverse square law relationship, similar to what you guys got for gravitational field strength. If you can't handle it, tell me, so then I'll help you out. If you get the answer, just type it in. It's very similar to like gravitational field strength. Remember that G1 on G2 equals R2 squared on R1 squared. It's very similar. Okay, 0.36. Let's check what the reduction is. Okay. Yeah. Anyone else got the answer? Because electric field strength also obeying the inverse parallel. It's the same charge. Electric field produced by the same charge. This is like E1. I can say E1 is KQ on R1 squared. E2 is equal to KQ on R2 squared. Therefore, I can write E1 on E2, R2 squared on R1 squared. Okay, 2.2. Okay. So we're looking for R2. So E1 is 40, that's 12. It's quite possible they can give a question like that. Divide by 12 and get the square root of that. Yeah, 2.2. That's good. Danuka, Deshan, yeah, 2.19. That's correct. Yeah, 2.2, 2.19. Okay. The direction, when you find in the direction of the electric field, always assume there's a positive test charge in space so that you can find it. So the electric field strength between two parallel plates. The reason that two parallel plates comes very handy because the field is uniform. None of these cases, the field is not uniform. It's same as the gravitational field. So the electric field between two parallel plates distance d. This is, let's say this is a high voltage. The electric field strength is given by the potential difference between that and that divided by the distance. So potential difference is we treating as 1 is 0 divided by d. So the field lines, guys, always going from positive to negative. If it is a positive charge, it will experience a force in the same direction as electric field. But if it is a negative charge, the force will be in the opposite direction. For a positive charge, it will be parallel. Parallel to electric field. Force on a negative charge is opposite. Can you say that's the direction? Okay. The force on the charge, again, Q times E. The work done by the electric field. On the charge, W equals F times D. But again, E is P on D. Therefore, the work done is Q times C. Sorry, yeah, Q times B. Sorry, Q times B. P is the potential difference. Okay, that's equal to change in kinetic energy. Work done by this net force. This is the work energy theorem. Change in kinetic energy. So therefore, initial kinetic energy, let's assume 0. So therefore, we can say Q times V equal to half mv squared. M is the mass of the charge. Just do a couple of questions. If you look at electron gun scenario, you have a hot filament. This is the filament. Electrons are shooting. And then you put a very high voltage here. So the electron can go through it. Let's say this is 5,000 volts. This is 0 volts. The electron can come in, speeds up, go through it. Okay, so that's about 5 centimeters or something. Find the electric field strength. Electric field strength, guys, the unit wise, either volts per meter or newtons per coulomb. If you ask you to find the electric field strength, you just simply do delta V on D or V on D, which is 5,000 divided by, convert centimeters to meters. That's how you find the electric field strength. Oh, yeah, sure. Yeah. Yep, okay, yeah. Yeah. I'll put the video anyway. That's 1,000 times 10 to the power 2, 10 to the power 5 volts per meter. Okay, next part of the question, find the force on the electric charge. force acting on the electron. Q times E. Okay, Q times E. Find the acceleration of the charge. So just simply Newton's second law. The mass of electron, guys, 9.1, negative 31. Times 1.6 to 14. Get like hang on. That's the mass. That's the acceleration. That's the force. Sorry, I just made a mistake there. $31. 14 divided by 31. So acceleration can be quite massive. 10 to the power 16 meters per second square. And part 4, find the exit speed of the electron from the electric field. It exits from the field. So in that case, you can simply use W Q times V. Otherwise, you can do one of the Suvet equation as well, because you know the acceleration starting speed is 0 and the distance is 5 centimeters. You can do all that, or you can simply use half mv squared. Don't mix up the two. That's the speed, that's the potential difference, in fact. 2Q times V over M. The potential was 5,000. 9.1, negative 31. If you make an error, if you get a more than speed of light, most likely there is an error. Times 5,000 divided by 9.1, negative 31. You get like 4.2 times 10 to the power 1, 2, 3, 4, 5, 6, 7 meters per second. Okay. We'll talk about the why electrons having a parabolic path. Whenever the particle enters into electric field, do not use slap rule, that's only for magnetic. The gravitational force is insignificant because of the very light mass here. That's the field. Let's say you're shooting the electron with a certain speed. When you shoot the electron, once it enters into the field, it will experience a force, downward force. Oh, okay, maybe I'll swap the directions. I can put other way, that's fine, but just for the clarity. The electron will experience a force, my electric field should be other way, okay? Electric field is always from positive to negative. Now we know that electron will go through parabolic path like that. The question is, why you get a parabolic path? It's easy to explain because you're shooting the electron horizontally. Electron enters perpendicular to the electric field. So there are no horizontal forces. Perpendicular to the electric field. It will experience a constant force. Constant electric force. Downward. F equals QE. Or towards the positive plate. Toward the positive plate. The force is Q times E. That force causing the particle to accelerate downward. At the same time, electron try to maintain its horizontal velocity because there are no forces in the horizontal direction. Like projectile. you had to mention this constant force. Did I mention anywhere? It enters perpendicular electric field, it will experience a constant electric force. Yeah, that's quite important. Vertical acceleration and constant horizontal velocity causes the charge to move on a parabolic path. That makes sense, guys? It's a combination of the two. Okay. Vertical acceleration increases over the time. No. Vertical acceleration stays constant. The speed increases. Say when the particle enters. So that's just concentrate on the speeds. Yeah, your horizontal velocity stays constant. Vertical velocity gradually increases. So that's your vertical velocity 1. As a result, it will try to travel direction like that. Now think about still trying to maintain the horizontal velocity, but the vertical velocity is increasing because of the acceleration. Constant acceleration, remember constant force, constant acceleration. It's pretty much like your projectile. It goes like that because it's have a more bigger component now. That's your resultant velocity direction. And then again, horizontal velocity remain constant, the vertical getting bigger. So now it goes like that. And then if I exaggerate more, as horizontal remain constant, vertical getting bigger. If you look at the path, you can see why it's going to be go in a parabolic path like that, because of your vertical acceleration. Yes, it's pushing, you're speeding up downward, but horizontally stays constant. Yeah, no worries. I'll put this one on the. Do you guys want to queue a quick few questions? And also balancing the electric field with the gravity. There's a Millikan type experiment. Your gravitational force is same as the electric force. That's one situation. Shall we try that one? Question 22 for page 22. Shall I give the break now, guys? What do you think? Shall I give you the break now? 15 minutes? That was page 22. You guys will meet up again 7:30? Yeah, okay. 7:30, okay. We'll meet up again 7:30. Okay. Just have a quick bit of break. Yep. Now I'm recording.
Good, thanks.
Yeah, I think I missed about 15 minutes. Anyway. Okay. So then you can see the force is up. So as a result, the particle will go through a circular path because the force acting on the charge is always perpendicular to the direction of the motion or direction of the speed. Okay, so you have to say when charged particle enters perpendicular to the magnetic field, a constant force It's very important to say constant force. X. This is the QVB. X perpendicular to the direction of the motion. Because of the force is perpendicular to the direction of motion, work done along the direction of the motion is zero. Therefore, there is no change in kinetic energy. Since the force is perpendicular to the direction of the motion, so there is no work done that way. Motion direction is zero. The work done by the force on the charge along the direction of zero. Therefore, the kinetic energy remains constant. The speed remains constant, not the velocity. The force acting on the charge become a centripetal force. So this causes the particle to move on a circular path. The most important words, guys, constant force, and the force is perpendicular to the direction of motion. These are the very important words for the exam, guys. So there is no change in kinetic energy. Kinetic energy of the charge remain constant. Speed remain constant, not the velocity, as centripetal, and that's the circular path. Okay, so you get, maybe we'll pick some question and quickly do it. It's a combination of electric field and magnetic field type questions. Could I put some questions? Oh yeah. Can you guys try question in page 38 very quickly? Page 38. Again, coming back. Page 38. Question in page 38. Yes, the prints. Just go through. Now, for the DC motor, you guys be familiar with the function of the split ring commutator. Say that it reverses the direction of the current. Therefore, the forces will reverse every half a rotation, which enable the coil to rotate continuously in one direction. So the question in page 38 is a combination of electric and magnetic fields. So proton is a proton source, is shooting through, enters into a magnetic field. The magnetic dots indicate the magnetic field is out of the page. Hey, guys, for DC motor, only split rings, okay, only the commutator. There is no slip ring for DC motor. So keep very clear. It's a motor, converts electrical energy into mechanical. So there is only a split ring, nothing to do with the slip rings for year 12. So we don't need to worry about that. That's the path. So they're giving that to be 10 kV. So to extend that equations, guys, so centripetal force become the centripetal force, mv squared on r. Then you get this radius, mv on qb. That's the radius of the circular path, mv on qb. That's 20 centimeters. The first question they ask you, calculate the strength of the electric field. Strength of the electric field is delta V on D, so just say V on D. V is the potential difference, not potential. 10,000, 20 centimeters. 100 divided by 2, that means 50. To the power of 4 volts per meter, okay? Volts per meter. Next thing, part B. Calculate the speed of the proton as it exits the electric field. Work done. Half mv squared. That's electric field was 10,000. Half times the mass. Mass was, as a proton, 1.7 negative 27. And then solve for speed, v. You should get a value of 1.4 times 10 to the power 6 meters per second. The next question, they ask you to find the diameter or the radius of the circular path. Okay. Okay. Yep. Can you guys go through and find the radius, guys? I think that's quite easy, yeah, everyone? You show the right answer for B. Which part B? The speed. Oh, I didn't check it. I just write down the answer. Double check. That's where I think I found the answer from. So Q is, I know Q is that's a proton. The potential is correct. Half mv squared. Let's see. V equals 2 times 1.6 times 10 to the power negative 16. 10,000 divided by 1.7, 27, square root of that. Okay. Yep. 1.6 negative 16 times 10 times 10 to the power 3. Divide by 1.7 negative 27, and then get the square root of that. 4.3, isn't it? 1, 2, 3, 4, 5, 6, 7. 4.3 times 10 to the power 6, 7. Okay, double check any numbers. Different 20 centimeters. Q times V, half mv squared. Yeah, it seems like 4.3. Double check. Should be. Yeah, I think it's a different answer. Double check with that. Yeah, it could be my answer was wrong. 2018, this was 2018 exam. Maybe just quest move on to the. Okay, I'll double check the answers. Question number 1. Q times V, that's correct. Half mv squared. Anyone got different answers for that? 1.4 times 10 to the power 6. I double check.
I got 3.07.
1.6 times 10 to the power negative 19 times 10 to the power 4. Negative 19 times 10 to the power 4 times by 2 divided by negative 27 square root of that. 1.37 isn't, yeah, 1.37, that's correct. 1.37 times 10 to the power 6. Yeah, I think that's 1.37 10 to the power 6. Yeah, that's 1.4 is correct. 1.4 times 10 to the power 6 meters per second is correct. Yeah, I think I got it. That's 10,000. So 1.6 times 10 to the power 4. Yeah, I think that's correct. 1.37 10 to the power 6. Yeah, I just double check again the weak answer. It's correct. Okay. So the radius should be, because if you guys want to practice when you're revising, you can write it mv squared on r, and then r equals mv on qb. The mass is 1.7 times 10 to the power negative 27. The speed was 1.37. Use that exact number if you can. Divide by 1.6 times negative 19. The strength of the magnetic field was 2 times 10 to the power negative 2 Tesla. So when you simplify that, you should be getting around 0.53. Okay, but I'm doing the square root way. Is that right? What do you mean by square root way? I mean, the way that I'm written here. Yeah, should be. That's 10 to the power 4. Yeah, so I'll double check. 2 times 1.6. Negative 19, yes. I just made a mistake there. Here we go. 2 times 10 to the 1.6 times negative 19 times 10,000 divided by 1.7. Yeah, maybe there was an error there. Okay. All right. Now, proton and electron, they both have the same charge. Yeah, negative 19. The charge should be the same. The charge, yeah, I put the wrong value before. Yes, that's correct. Okay, anyone not getting that radius, guys? Radius is supposed to be 0.53. Okay, I think I just highlighted and put, we just go into magnetic flux. I just put that in yellow. That's the 3-mark answer for the split ring commutator if you need. Okay, we just move on to flux. Everyone know flux, right? So magnetic flux, it's just the amount of field line going through a certain area. Magnetic field passing through a certain area. Now, some people forgot that when you have a coil like this, always remember flux is 0, guys. When it's flat, there is nothing passing through that coil. No magnetic field linking through the coil area. Because after that, I think everyone knows it, but yeah, some people forgot completely. The flux is 0. Magnetic flux is 0. The unit for flux is Weber. Okay, so you get the maximum flux. When it's vertical, you get the maximum flux. Maximum, because the field lines are nicely linking through that area. Now you guys, okay, so now we just talk about Faraday's law. Faraday's law, he's the guy who started to understand the induced EMF. How do you produce electricity? Induced EMF, I mean, you producing a potential, electric potential. Induced EMF, he said that proportional how much flux you changing or how quickly you changing, rate of change of flux. Rate of change of flux. Okay, how quickly you change the flux. And then combining with the number of turns in a coil. So he modified, this is the equation for average EMF. The negative sign coming from the Lenz's law. Number of turns. Okay, this is negative sign. It's coming from Lenz's law. Okay, Lenz's law. Let's find it out. You have a magnetic field. The strength of the field is 0.5 Tesla. You have a square coil. With number of turns 50. The magnetic field was reversed, and then the diameter is 6 centimeter, or maybe say 10 centimeter diameter. Out of the page in 1.5 seconds. Find the average EMF. Okay, so you guys understand the question? So you have a field going into the page, you're reversing it. Yeah, reversing it in out of the page. Oh, you didn't get 0.53. Sorry. You got it before or not? You didn't get it.
Yeah, I got it after that.
You got it?
It's the wrong. Yeah.
Oh, good. Okay. Okay, guys, give it a try. Find the average EMF. So the average EMF, you have to consider like an angle flux going into or out as a positive. I mean, cos 0. Remember the angle. So if I try to draw it, initially magnetic field is going like that. We're talking about relative to the area vector. You can consider your area vector originally in the same direction. Or maybe you can say opposite to that. You can say area vector was like that. The magnetic field was like that. So the angle in this case is like 180. And then you're swapping back to parallel. That's your area vector. Angle in this case, theta equals 0. Okay. So we need to find the final flux minus initial flux. The final flux, I would say B times A, that is pi times the radius was 5 centimeters, convert into meters, pi r squared times or 0.5. This is the area, pi r squared. Pi r squared. Okay. So you can find that area. So in here, it's more like negative BA. Same number. So what I'm trying to say is it's going to be double. Connect to a disc motor with the slip rings. This is the question that we had last time. If you connected a C supply or DC motor with slip rings, the slip rings not going to change because slip rings will stay constantly connected to the battery. So it can't reverse the direction of the current. So you will see the same consequence as like this oscillation and come to a stop, because the slip rings will not reverse the direction of the current flow in the coil. The radius is 10 centimeters. Okay, yeah. Yeah, so because even if there is no friction, ideal case, it will oscillate forever, but we know that because of the friction, after a few oscillations, it will come to a stop where the torque is 0. Yeah, that's correct. That's same as when you're connecting directly your coil without the split ring commutator. So because you have that oscillation, like provided that you had enough momentum to pass through that vertical position. Because last year exam, they tends to give marks for people saying that if you, what's the question was, if there is no slip rings, what will happen or something. So basically say that it start to rotate, it basically stop vertical position. But then everyone argues like oscillation and then come to a stop should give the marks. Yes, they agree that. So provided that you have enough momentum to pass through that point, even when you connect the slip rings, the same thing, because the current direction is not changing, it starts to rotate. Now, if there is, so you have a momentum, certain momentum that will pass through the point, now it's going to lose that energy because the pivoted points are not ideal. There are some friction. As a result, finally it's come to a rest position. So the value, double check these values by 3.9293 times 10 to the power negative 3, 3.93, 10 to the power negative 3. So the change in flux is going to be, so this is the final, this is the initial flux, this is the final flux. So the change in flux is going to be the difference the final minus initial. The final flux is going to be 3 point, that's a positive, 3.93, negative and negative 3.93. So overall flux, that's going to be times by 2. You get like 7.85 negative 3 Weber. And then you can sub it into the equation. Average flux going to be number of turns, 50. We take just the magnitude, although we're getting a negative answer. Now this is a situation you don't change, divide by 4 or anything. We just get the time it takes for that change, 1.5 seconds. That's the time it took for the whole change. 50 divided by 1.5. Get like 0.26. Take the magnitude of that. Yeah. No, because when you come to rest in the horizontal position, there will be a torque acting because the current is still flowing. Whenever the torque acting starts to spin. In a DC motor, is the purpose of the reversing the current to prevent the planar beam from being parallel to the field? No. No, the idea of the reversing the current, if we don't reverse the current, okay, we'll quickly run through the DC motor. So the DC motor without, let's say, I don't have a slip ring or split ring commutator, sorry. I just connected my coil directly to the battery. Two ends, I just connected to the battery. The current is flowing. Let's say ABCD. Then what will happen? The coil will start rotating anti-clockwise because the torque is acting. That's fine, that's good. The coil remains start rotating. Let's consider a situation where it's rotated 180 degrees. Okay, 180 degrees. Now, this is where we are expecting our split ring commutator to reverse the direction of the current. If the coil rotated 180 degrees, let's assume there is no tangling or anything, so it's still the side X is connected to the positive, side Y is connected to the negative, but the coil has flipped completely the other way. Your AB is here. ABCD is here. Now side AB is connected to the, so that's X, that's Y. Positive. Now label the direction of the current and work it out the forces. So that's force going to be down, correct? Down, this is up. Because we expecting the coil to rotate continuously anti-clock. But now what's happening, the side AB before the force was down, still the force is down. Side CD force is up, still up, before up. But the rotation, the way that they oriented, the rotation is clockwise. We don't want that to happen. If that happens, the coil going to oscillate and eventually come to a stop. We don't want that. So to avoid that, what you do, soon after we pass that point, so this is not good. So the coil eventually come to rest at vertical position where the torque is 0. So that's come to rest. What we need, soon after it passed that vertical position, we want to stop the current from A to D to D to A. So when it's swapping the direction of the current, so this is a split ring commutator. This is the commutator. So that you started there as before usual, as usual. So A, B, C, D here. You have these two rings, they're solidly connected to the coil. They rotate with the coil. And then you have these graphite blocks, they are not rotating. They are the one giving that electrical contact to the commutator. Now look at the current flow. Current is going A to D. And the forces are like before. Force down, force up. Rotation is anti-clockwise. When it's moved vertical, when the coil moves vertical, the two half rings looks like that. So there is a momentarily it disconnect from the power. There is no current flow. Momentarily there is no current flow through the coil. The power supply. Because the two half rings, the gap between the two half rings nicely aligned with that graphite blocks. So there is no current flow. This is momentarily, there is no torque, no forces. It's like a just split second, instant second, no forces in the coil. But the coil will continue to move because of the torque. So now it's DC here. Further, due to its momentum. Then what will happen? The two sides, if I say two sides are P and Q, this is connected to the positive and negative. The P will connect to the negative side, Q will connect to the positive side. They swap the direction. So I just look at the extreme case. Let's go back 180 degrees rotation. This is after you. This is 90. This is 180. The coil will be like that. Your DC will be here, DC, BA. We saw the problem before without the split rings. It's going to rotate other way around. Now you connect the slip rings are swap the side. So before PQ, now it's become QP because it's moving with the coil. But the two graphite blocks, they are not moving. Still that one is positive, this is negative. I connect to the battery. Look at that, the current now the side, the current flow is from D to A. Before was A to D, now D to A. That's the whole function. So the function is to reverse the direction of the current. So the forces will be swapped on each side. Now look at the force on side CT. Force is down. Before force was up. And here force is up. That force was down before. We want that current to swap and therefore the forces will swap the direction. As a result, the torque will be in the same direction. The rotation will be in the same direction. The rotation will be in the same direction. Yeah, there is no force because momentarily it disconnects from the power supply. Force is maximum when the coil is, hey, force is always constant. Force is, it is the torque. The two forces on either side of the coil, these forces always stay constant because they see the magnetic field is always perpendicular. These forces not going to change. They're not changing with the side, far side. Yes, they do change with the angle. At the moment, the force is zero here. And if there is a current flow, the force becomes maximum because now current, no current. But if there is current, the force becomes maximum. But not these two sides. Those two sides always see the force is the current flow is perpendicular to the magnetic field. Okay. Where are the forces acting when the coil is? There are no forces because momentarily there is a disconnection. There is no current flow. When it's vertical, because your gap is aligned with the brushes, there is no electrical contact. So there is no current through the coil. So momental, it's a very split second. So there is no force. Yeah, so there are no forces. You're asking the question, where are the forces? No forces. How come I have force? There is no current flow through it. Okay, we'll quickly have a look at the lenses law, guys. How are we going with the time? All right. The Lenz's law, as you guys know that if I move a magnet through a coil, maybe. How do you say? Sorry, there is a magnet. So there is a coil, but it's not a solenoid as such because it's not connected to the power supply. But it's connected to the ammeter. Now Lenz's law states that if there is a change in flux, we know that when there is a change in flux, there's an induced EMF. That's coming from Faraday's law. The Lenz's law states that because of the change in flux, the induced current in the coil producing a magnetic field to oppose that change. So that means if I move the magnet towards it, you can see the magnetic flux through the coil is increasing. We have to give the direction. The V guys always give a direction. That's the direction of the magnetic field. So when the magnet moves towards the coil, have a look in the research exam. They're always giving a direction. The direction they refers to the direction of the magnetic field. When the magnet moves towards the coil, magnetic flux through the coil increases. Okay, so when there is a change in flux, there is induced EMF. Okay. The change in magnetic flux induces a EMF, and also it induces a current. Now, so according to Lenz's law, if you want to write Lenz's law or not to write, that's fine. But Lenz's law, the magnetic field produced by the induced current increases to the left. To oppose the change. To oppose the flux change. That means it's trying to make it zero. These are the induced magnetic field. It tried to make like a north pole there. Induced magnetic field. So then you have to use the right hand grip rule. So I need a magnetic field. I'm using my thumb for the magnetic field. This is the induced magnetic field. And curling my fingers around. Your thumb should be pointing towards the induced magnetic field. And then you curl your fingers around the coil. Somewhat out like that. Then you can figure out what direction the current should be flowing. So that's the direction of the current flow. Like that. And then you can trace back here. The current through the ammeter goes X to Y, through the coil goes from Y to X. So you have to be very careful to see what they're asking for. That makes sense, guys? Yeah. Shall we do one couple of questions and then we'll wind it off? Hey, can you guys tell me what's happening here? Page 44. What I will do, since we couldn't finish special relativity and the motion a bit, maybe I'll do that one tomorrow morning, motion and the special relativity, and the graphing. I think waves is the one that I feel need for you guys to brush up. I think light and matter, hopefully you guys are still fresh. Let's see when I get another time. I'll go to light and matter and the waves, but I'll focus tomorrow morning on the motion, special relativity, and the graphing questions. Can you explain that? Okay, so I'm moving the magnet towards the coil. Therefore, remember the vector direction of the magnetic field in front of that, the bar magnet is to the right. So the strength of the magnetic field is increasing in the coil. So when the magnet moves towards the coil, magnetic flux through the coil is increasing. Now, therefore, you have this induced magnetic field is happening onto the left to oppose that. Then we're trying to figure out the direction of the current in the coil. What do? You point your thumb in the direction of the induced magnetic field. Your thumb should be in the direction of the induced magnetic field. Feel like if you have a pen or something, pretend like you're trying to grip that pen. Then the fingers will tell you what direction the current is flowing. Keep your thumb in the direction of the magnetic field and then grip your hand like that. And the fingers will be curling in the direction of the current. And that's why I label my current direction there. And then you follow that path. Follow that path to see what direction the current is flowing. Okay. You guys okay with that? Then so slow. Maybe I'll do whatever the remaining one plus the graphing tomorrow morning. And then, because if I try to go rush everything, I mean, you guys are not getting much. I'll go a bit slowly and then finish it off the leftover thing, motion plus special relativity, springs, and then I'll do graphing as well. And then we'll find a time to do, maybe I'll just do half an hour revision, and then the rest remaining time for the paper kind of thing. Maybe, I don't know, maybe I'll find time. Okay, hey guys, what's going to happen here? When you turn on the switch, graphing means like the uncertainty questions. So I'll find different variables like an independent, dependent variable. Yeah, because that's quite a bit of marks. We haven't done many graphing and looking at the error bars, line up best fit, calculate the gradient, and answering whatever the questions they're asking. Okay, what's going to happen here? That's a ring there. So the coil around. When you turn on the switch, I need to go through the transformers, power transmission, power losses. I think quite a bit. So maybe I go a little bit slower to finish it off. Those are the sections people are having trouble with. And special relativity. If you are across all that, then it's okay, not to worry. So when I turn on the switch, the current will flow through. And suddenly, so if I use the grip tool again, this is the current magnetic field produced by that solenoid part. I can see there's a magnetic field going on. It's increasing field. When switch is turned on, the magnetic flux through the ring. This is the ring, okay. Increases. So according to Lenz's law, an increase in magnetic field acting downwards. To oppose the change. So essentially there will be a north pole. So this has become a north pole. So the ring creating its own north pole. So north and north means repelling each other. Because the top end is free, what will happen, ring will fly away. Ring will fly. It will fly away. Have you guys done this experiment at school? Some people must be doing it. Yeah, this sudden change. So it's a sudden switch turn on, magnetic flux of the coil increases, like momentarily, okay? Because if you keep it too long, the flux becomes constant, because soon after you turn the switch on, the magnetic flux increases, the magnetic flux will be coming down to opposite. At this node, suddenly the ring will fly away. Okay. Why does the ring go up? Could you okay, because you have a north pole there. There's a magnetic repelling force here. That's my wiper. So you have this solenoid, right? you turn the switch on, suddenly there is a current flow, and it's producing a north pole there. If I use the grip rule, I mean curling my fingers around, and then you can see my thumb is pointing up, so that there will be a north pole there. Now just imagine that ring is sitting up here. So it's like a good, this is like a good ferromagnetic, like a soft iron, as well as magnetic flux can nicely link through. So sudden increase in that magnetic flux is seen by the ring. Ring trying to oppose that by producing its own current to produce a magnetic field opposite way. So that means at the bottom end, it's creating its own north pole. So it's the same reaction like north and north. Okay, so it's going to repel each other. Okay, I think most of the labs, some school lab, they have this setup. Okay, guys, I'm pretty tired. I'll stop there. I'll start tomorrow morning, 9 o'clock. Whoever can come in, just come in. But I will finish it off the power transmission, transformers, generators, plus special relativity and motion, and the springs. And then definitely find some time to at least go through a few graphs, different aspects of graphs, and draw in the error bars, line of best fit, and all that. Because if I dedicate one big slot for the graphing, it's going to be very boring for you guys, very difficult for you guys to get the motivation for lots of graphs. So at least we have some time to plot a graph, plot few graphs. Okay. Is that okay, guys, if I wind it up? Yeah. But I left lots of questions. If you guys can have a look and do those questions just for a revision exercise, that would be good. Any questions? If you guys are not sleeping, still there. Okay. All right. Yep. Okay, no worries. Okay, see you guys.
Thanks, sir.
Thank you, sir.
Bye.
Thank you, sir.
Thanks, sir.
Thank you,
Thank you,
sir.
sir. Thank you, sir. Thank you.
Thank you, sir.
Thanks, sir.
Yeah, thank you, sir.
Bye.
Thank you, sir.
Bye. 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 See you guys. I'm going to knock this one off.
Thanks, sir.
Bye.
Thanks, sir.
Goodbye.